In the last video, we looked at what happened whenever we added two numbers together that have the same exponents. And we've seen that in that case we had to normalise the result. That is, we had to ripple a value of 1 up through the exponent, and we had to decrease the mantissa by a factor of 2. And that will always happen whenever we have exponents, numbers which have got the same exponents. Now in this video we're going to extend our number of additions that we can do, and we're going to look at adding numbers that are in different exponent ranges. So let's look at a few examples, and from those examples we will build up a general algorithm that will allow us to add all numbers. Now in the first page here we're going to look at the base 10 because that's what we're used to seeing most in our daily lives. So let's say for example we had 80,000 plus 4,000. We know that's going to give us 84,000. So that can be written as 8 times 10 to the 4, and this one here can be written as 4 times 10 to the 3. So our algorithm said that we had to take the smallest exponent and make it the same as the largest exponent. So it means that this 10 to the power of 3 here becomes 10 to the power of 4. But of course, in order to keep the arithmetic correct, it means we're going to have to decrease this value here by a factor of 10. So this is going to be 0.4 times 10 to the power of 4. So it means that we can now add these two together. So 8 plus the 0.4 is 8.4, and the exponent is 10 to the power of 4. Now we've seen that the ex minus ey, so that's the largest exponent minus a smaller exponent, is 4 minus 3, which is a value of 1. So in this example there's an exponent difference of 1. Now if we were to write this down mathematically, what we would be saying is we're going to take the mantissa for x. So this is going to be the mantissa here for x, which is the 8. And we're going to take the mantissa for y. So the mantissa for y again is the 4, but we're going to divide it by the factor of 10 to the power of ex minus ey. So it's 10 to the power of 1 in this instance. So it's just my upon 10. So that's just the 4 divided by 10, giving us the 0.4, and the value that we're going to multiply it by is our 10 to the power of ex. Now in the decimal system here, in order for it to be normalised, the value for our m here, which is this final m within this bracket, has got to be greater than or equal to 1 and less than 10. So in this instance here, we have that occurring. We have 8.4 times 10 to the 4. Well, the 8.4 is between the number 1 and 10. So it means that the final result for this is 10 to the power of ex times what is inside that bracket there. Inside that bracket is just we'll call it mr. So in this instance here, we don't need to do any final normalisation. Now let's look at a second example here. Let's say we have 95,000 plus 7,000, and that gives us 102,000. So again, we can write this as 9.5 times 10 to the 4 plus 7 times 10 to the 3. Now again, we have to make the smallest exponent equal the largest exponent. So it means that this 7 times 10 to the 3 is going to become 10 to the 4, and the 7 will have to be a value of 0.7. So we're doing the same process above as we did above there. So whenever we add both of these together, we're going to have 10.2 times 10 to the 4. But you can see here now that this is not normalised, because this number here has to be a number between 1 and 10, but the number here is actually greater than 10. So it means that whenever we do the normalisation, we're going to have to make this smaller. So that's going to have to be 1.02, So if we make that 1.02, we're going to have to make this one larger. So this is going to be 10 to the power of 5. So our final normalised answer is 1.02 times 10 to the 5. Now again here we can see that our ex minus ey is equal to the largest exponent, which is 4, minus the smaller exponent, which is 3, is a value of 1. So it's the same exponent difference in this case. So again, this line here is the same as this line here. We've got our mx. We are shifting the value of our my by 10 to the power of ex minus ey. And finally we multiply it by 10 to the ex. But again, we've said here that the result here is actually greater than 10. It's 10.2. So if the result is greater than 10, we then have to normalise the answer. So normalising the answer, we take this value here, which we call mr, and we divide it by a factor of 10. So this is us dividing the 10.2 by a factor of 10 to get 1.02. But then we're going to have to increase the exponent by a value of 1. So again, you can see we've increased the exponent here by a value of 1 from 4 to 5. Now, that's an example of the two possible normalizations that we're going to have to do whenever we do addition. But that's for a decimal system. Let's have a look at the same examples, but let's have a look at them in terms of a base 2, which of course is what we're going to be using. So here are two similar examples which have been done to the base 2. Now before the end of the video we will put these values into the Excel VBA tool. So let's look at the first one here. 4.8 plus 10.4 giving us 15.2. So the 4.8 can be written as 1.2 times 2 to the 2, and the 10.4 can be written as 1.3 times 2 to the 3. Now in order to add these together, we're going to have to make sure the exponents are the same. So we're going to make the smallest exponent equal to the largest exponent. So this 2 to the power of 2 becomes 2 to the power of 3. But now we've multiplied this by a factor of 2. In order to keep this number the same, we're going to have to divide this by a factor of 2. So that's going to be 1.2 divided by 2, which is 0.6. So now we're in a position where we can add these mantisses. So 0.6 plus the 1.3 is 1.9, and that's times 2 to the power of 3. So you can see here that the final result is actually in a normalised form because the value for this final mantissa is a number that's greater than 1 and less than 2. So you can see that the exponent difference here is a factor of 1. So e to the x is the 3, e to the y is 2, 3 minus 2 is a value of 1. And what we've done above here is modelled in this little equation. So mx is the mantissa for x, which is 1.3, and we're shifting the value for my. So my was 1.2, but it's now divided by a factor of 2. Now in this instance here, the factor of 2 is 2 to the ex minus ey. So ex minus ey is 3 minus 2, which is 1. 2 to the power of 1 is just a value of 2. So this little line part here is the 1.2 divided by the 2, giving us 0.6. And we've got our final e to the x. Okay, so that's 2ex. Now, as we said, the value here for the mantissa is greater than or equal to 1 and less than 2, so it's 1.9. So it means the final result can be written as everything that's inside this bracket, which we could call mr for the result of the mantissa, times 2ex, that's 2ex, so this is the final result. So in this instance here, we don't have to do any final normalisation in order to get the final result. Now let's look at the second example. 4.8 plus 14.4 is 19.2. So this again is this number here, and this one here is this number here. Now we have to make the exponents the same, so this 2 has to go to a 3, but if the 2 goes to a 3 here, we're going to have to half this value, so that goes to 0.6. We're now in a position to add them. 0.6 plus 1.8 is 2.4. times 2 to the 3. Now you can see in this instance here that this is not in a normalised form because the value here is greater than 2. And we wanting the mantissa to be a number greater than or equal to 1 and less than 2. So again, in this instance here, our ex minus ey is 3 minus 2 is a value of 1. So the exponent difference in this example is a value of 1. And this equation here is the same as this one, and it defines exactly what we did in this line here. But now we've got an extra part here. We've got the normalisation of this because our m is greater than or equal to 2. So in this instance here, what we have to do is make this a number which is between 1 and 2. Well, we can do that by halving this number, so that becomes 1.2. But if we halve this number to keep this number the same, it means that the exponent is going to have to go up by a factor of 2. So that goes up to 2 to the power of 4. So the little bit of mathematics that describes this is going to be mr upon 2 times 2 to the ex plus 1. Now, what we see here is the ripple through into the exponent. So this is the extra value of 1 which gets rippled through into the exponent. And when we ripple through into the exponent, we're going to have to make the mantissa smaller by a factor of 2. So let's look at the final example, which is an exponent value which is greater than a value of 1. So here is our final one here. In this instance here, we're going to have 4.8 plus 819.2, which is 824. So this number can be written in this form. This number here can be written in this form here. Now in order to do the addition, we have to make sure the exponents are the same. So this exponent here has to go up to 2 to the power of 9. So it's got to go up by a factor of 7. So if this number here goes up by a factor of 7, then it means that the 1.2 has to be divided by a factor of 2 to the power of 7, or equivalent to 2 to the power of the largest exponent minus the smallest exponent. So that's 2 to the power of 9 minus 2, which is 7. So we can now rewrite this here as 1.2 upon 2 to the power of 7 times 2 to the 9 plus 1.6 times 2 to the 9. Now we can add these two numbers together. So whenever we add these two numbers together, we get this number here, 1.609375, and that's all times 2 to the power of 9. Now again, the exponent difference here is the 9 minus 2, which is 7. And we've got the same equation here as we had in the previous example. And this describes what we've done above. And in this example, you'll notice that the final answer is a exponent value, is a mantissa value, which is greater than or equal to 1 and less than 2. So it means that there's no normalisation required in this particular example. We're going to have the final result, mr, and it's going to be times 2 to the ex. Now we don't need to do the other example here. We can see that if the value for the mantissa is greater than 2, then we're going to have to normalise. And we see them be normalised by rippling a value 1 through the exponent and dividing the mantissa by 2. So the same thing would happen here if this value here was a value greater than 2. So let's look at the final page here, and we'll see the final algorithm that we can use to add all numbers. So here is the general algorithm that we're going to use in order to add all numbers. Now I've replaced the value 2 with a value of beta just to generalise the equation. So if we had x plus y, then we're going to take the mantissa for x and we're going to add on the mantissa for y. But we can't add the mantissa for y until we have divided the mantissa out by this factor here. Now we've had to divide this mantissa by this factor because we've had to increase the exponent for y. So we increase the exponent for y to make it the same as the exponent for x, and then we've got to decrease the mantissa by that same amount. So everything inside the bracket here can be written as MR. So finally we're going to be left with MR beta EX. And that's just what we've got written down here. The MX plus the MY, so this plus this is given this term MR. Now the MX, we know that the numbers that we receive are normalised, so the MX is greater than or equal to 1 and less than 2, and the MY is greater than or equal to 1 and less than 2. So obviously it means that whenever we add these together, we can get a number that's going to be greater than or equal to 1 and less than 4. So if we got a value for MR which is greater than or equal to 2, then we're going to have to ripple through that extra 1 through the exponent, and we're going to have to decrease the mantissa by a factor of 2. So the final result would be given by MR upon beta, and it would be times beta to the EX plus 1. Now the other possibility is that the value for MR is greater than or equal to 1 and less than 2. In this case here, we don't have any normalisation required, so we don't ripple the extra 1 through, and there's no change in the mantissa. So the final result, again, is just the MR times beta EX. So this is the algorithm that we can use in order to add any of our numbers together. So let's take the numbers and we'll put them into the spreadsheet and we'll see them working. If you get into the resources section, you'll find the Excel spreadsheet, so you can go ahead and open that up. And if you go into the Add Subtract button, then it will bring up our program. Now we want to go through a couple of the examples we've seen. So let's say we pick the first example, 4.8 plus the 10.4, and that's going to give us a value of 15.2. Now it's not exact because the answer in 32-bit is not exact, it's continually repeating. So let's have a look and we'll see what's happening here. We're going to be taking a copy of the two numbers, the y and the x. Now in this instance here, we're going to actually swap them round about because we wanted the ex to be greater than the value of ey. So it means that the y value becomes the x value, and you can see that happening here. The 1 0 here, you can see it's actually 1 0 down here, so the y value has become the x value. Now that would just be equivalent to us taking the 4.8 and putting it in that box, and taking the 10.4 and putting it in that box. Now we've got to then add on the hidden bit, so we add the hidden bit on here. And after we've added on the hidden bit, we're going to have to shift the value of y by the factor ex minus ey. So the ex minus ey is going to be a value of 1. So it means that this value here will get shifted along by a factor of 1. So the 1 0 0 will become 0 1 0. Now we can add both of these together, and when we add them together we're going to get this line here. So you can see here that the full stop is at this point here. Now we don't have a 1 here, so it means that there's nothing going to ripple through into the exponent. So there's no ripple through into the exponent, and there is no normalization of the mantissa required. So it means that the full stop is at this point here, and the mantissa is given by everything that is to the right of the full stop. So everything that's to the right of the full stop is this 11100. So the final answer here you can see is going to be 11100, 1100. So this is the final answer down here. Now we could do the same with the third example. So you can try the second example for yourself, and we'll go ahead just now and we'll look at the example number 3. So example number 3 was 4.8 plus 819.2, and that gives a number 824. So we've seen whenever we did this that the difference between these is a value now of 7. So it means that the value here, y, is going to have to shift by 7 places. So the 1, 0, 0, 1 is going to shift. So it's going to go 1, 2, 3, 4, 5, 6, 7 places. So it's going to be all the zeros here and then the 1, 0, 0, 1. And then when we add both of these together, we're going to get this number here. So again, you can see in this instance here that there is no 0 going, no 1 in this box. So it means that the exponent value doesn't have to get added a value of 1 onto it, and we don't need to do any normalization of the mantissa. So it means that the full stop is still here, and the mantissa value is everything to the right of that full stop, which is a 1, 0, 0, 1, 1, 1. So we've got 1, 0, 0, 1, 1, 1 here. Now the best thing to do is to put in some examples of your own and chase through the 1s and 0s and make sure you understand the normalization and also the shifting of this value of y. Now one thing to note here is that what's going to happen here whenever the exponent value is very large. So let's say, for example, we had we'd put a large number in. So you see the exponent value is 4, the difference, 7, 11, 14, 17, 21, 24, 27. So that can be a huge exponent value of a difference. But you'll notice here in this instance that we're going to have to shift this y value by a factor of 44. So that would mean that we're going to have all zeros in the actual mantissa for the 23 bits. So that would mean then that we're not going to get the correct answer. Well, that is right, we won't get the correct answer because we're only working in a 32-bit floating point system here. And what we're going to do is lose precision. So if this y value gets shifted all the way out of the 23 bits, as it shifts to the right, we're going to lose precision. Now we'll talk about that in a different video. It's just a note for yourself to see exactly what's going to happen when we shift this out. So this is a large shift, and we are interested in this large shift. So we've come quite far in this video, and we've worked out an algorithm that allows us to add every number. Now we're going to have to go in the next video and look and see how we're going to do subtraction. So thank you for listening. I'll get you in the next video. Goodbye.